being good, I hope.
Okay, I started recording to the cloud.
Sure.
Okay.
Okay, great. Okay, do you have any specific topics in mind today?
Yeah. Why don't we talk about the path integral?
Sure. Yeah, okay, that sounds fun.
Yeah. So I won't go into like calculational details that deeply right now, but like,
Sure.
wait. Let me connect to what I was the whiteboard. Give me just a second.
I'll create a new whiteboard called 3.1,
Okay.
and we can use that.
Could you like send me the ID?
Oh, sure.
Wait, you don't need to send me it. Let me just. Yeah, for some reason I think I'll just type it in.
Sure. There's an autocomplete, right?
So it's gonna take a while.
Sure, take your time.
So the reason why I wanted to talk about the path integral is I feel like it is the primary reason, I guess you could say, that physicists and mathematicians are different fields. Well, theoretical physicists, at least. Okay, okay, let's try again. So yeah, the reason is like the path integral has been super elusive in like definition. So wait, you send me the link through Messenger, right?
Oh, not really. Let me just.
Yeah, Messenger
yeah,
would be
WhatsApp.
better. Yeah, just send through Messenger.
Sure. Do people at MIT use Messenger more?
I honestly don't know.
I see. Yeah, okay.
Nice, thanks. Great. Okay, let's go. So like I think in some ideal world, if we could define path integral, then physics would be basically an area of study which is centered around using some very interesting functional analysis, or I guess some topic from analysis to solve problems in algebra and geometry. But apparently that's not really being done. Like the path integrals are like apparently in an ideal world, I guess. We will be able to use topics from analysis to define the path integral. And this would allow us to solve problems. By solve problems, I mean like proof stuff, I guess, in like geometry, topology, and algebra. But in the real world, this part really isn't working out, and physicists are doing this part, I guess. They're using something that isn't defined. Like that's the issue. So what's really happening is that there's the path integral, and there's geometry, topology, and algebra. And physicists are making conjectures,
Hmm.
or
Because the
like
path material is
motivating
not a
conjectures.
well-defined.
Yeah,
Hmm. Talking about things like supersymmetry, string math.
yeah. But I have to point out though that perturbatively calculating the path integral is defined,
Oh, okay.
and it was defined by Kevin Costello.
Perturbatively meaning the discretization or
Oh, perturbative in doing a perturbative expansion in like the
some
what
parameter.
interaction parameter, like in Feynman
I
diagrams.
see. I see.
This
Okay. Is this a recent development?
I don't know how it's not super recent, but it's not super old. It's actually pretty new. He wrote a book called Renormalization and Effective Field Theory, Kevin
Hmm.
Costello. So yeah, people who are interested should definitely check that book out. But yeah,
Sure.
yeah, you should. Yeah, you could like take a look at the book right now.
I see. Okay, that's interesting.
So yeah, I think maybe like you could go and look at what Witten said about the book.
Oh, okay.
Uh, Maybe you could look at the. Oh yeah. Let's look at the AMS bookstore link. Because Witten said
When I put,
something, and if you like go down a little bit,
I
okay,
see.
there's Witten's quote. So perturbative quantum field theory is accessible to mathematicians
Mm.
because of this book. So that part of quantum field theory has been made rigorous. But that is
Oh,
not a
okay.
rigorous definition of the path integral because the path integral contains all non-perturbative effects as well.
Mm.
So when Witten says hopefully to an eventual blah blah blah, he's usually saying that blah 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 is an unsolved difficult problem. Um,
Mm.
so yeah.
I see.
Anyway, coming back. So right now the path integral is just a tool that is used to motivate conjectures in math. And
Mm.
because you're using stuff that doesn't have definition, mathematicians aren't necessarily interested in those physics derivations that are basically used to motivate conjectures. And then
Mm.
mathematicians actually prove those. But as physicists, there are like a few rules to like working with the path integral. So I figured it would be interesting to like kind of deal with that.
Mm. What rules are they?
Yeah. Oh
What
yeah,
rules
the
are there
rules.
to?
I don't know. There are a few. Let me just write them down. So I guess like we should like. I guess it's really about. I think the essential philosophy is to assume that the path integral exists, and to consider what properties it would satisfy if it were to exist. So the path integral is basically an integral over the space of functions over some other space. So for example, if it were R2 to R, these are the functions. This is the space of
Mm.
functions. Then we will write integral omega is like integral d phi, where phi xy is a real number and x and y are real numbers.
Mm.
Um, okay, I guess number two, number two, method that is intuitive, but not really helpful for analytic calculations. By analytic, basically mean doing calculations by hand and not using a computer.
Mm.
is discretization. Where basically we take a lattice, so that would be xn ym with xn equals to n times a, ym equals m times b, a and b are real numbers, and then m are integers.
So A would be the spacing between
Yeah,
the grids, and B will be spacing as well.
yeah. And basically, the path integral is roughly speaking the limit as a and b go to 0, integrating over the 5 values at x, s, n, and y, m, and this is producted over all n and m. This obviously this is defining the limit isn't really that simple, but I mean, this is a pretty intuitive definition.
This is basically turning functional analysis into multivariate calculus.
Exactly, because multivariate calculus is well understood. Now, another method takes the dimension of the domain of the function and analytically continues it to not non-integer values. So let me explain what I mean by this. So assume that you basically have a function from Rd to R. And you're doing integral d phi. As it turns out, this might diverge in d is a natural number, I guess. But we take d to be equal to a natural number minus an infinitesimal. Integral d phi converges.
Is it? I've seen this treatment in the 4 minus epsilon regularization.
Yeah, this is just dimensional regularization.
Yeah, but I don't really understand why such a thing would work, though. What are the source of divergences when d is
okay? So the reason is actually due to the gamma function.
Oh.
If I recall correctly, the gamma function is a bit of a pain in the butt because like it's defined by the factorial, but like n+1 or something. Let me just you could like search the gamma function on Wikipedia right now. I guess that would be cool.
Let me just sure. I'll just split the screen.
I should really like write lecture notes on the path integral. Obviously, like that would not be for mathematicians. No sane mathematician will want to read it, but I feel like physicists kind of deserve a better treatment of the path integral. Okay, so gamma n is equal to n minus 1's factorial, I guess. And you can see that this like gamma n has poles at n minus 1 minus 2 ...
Right.
But let's see here. So we can see that it is not divergent at n not being an integer, right?
Yeah.
Like that's kind of the reason.
Oh, I see. Okay, that's quite remarkable.
And like I think a similar example of this was like sum over okay, another example, I guess, another way to see it, another example. I'm being a little bit vague here, but there is like this problem called the sum of all integers. And we could take s here. this obviously you can't calculate this equals infinity for s equals 1, but I think there is some sense. I'm not sure, but I think you could like input s equals 1 minus epsilon and get 1 over minus 12 if you do some kind of like
I've seen this treatment before.
physics math.
I think it looks like yeah. I've seen this treatment somewhere. I think it's zeta function
Right, yeah.
QFT. Yeah, I've certainly seen something like that. It's something like 1 over epsilon squared plus some terms minus 1 over 12.
Right, yeah.
Let me
So
try to find it while you
yeah.
continue.
I mean they are all the same thing. Yeah, so anyway, like yeah, any regularization method is either using some kind of version of a lattice spacing or some kind of version of dimensional regularization and analytic continuation. The more physical way to do things is lattice spacing, but the more I think useful and the more simple way to do it is using analytic continuation. But anyway, like this is necessary to do the path interval. I think that's pretty. I think everyone would agree on that. And it's even like it's even necessary in like free field theories. Because okay, even when the okay, so field theory. Okay, so this is a statement for people who know a little bit about quantum field theory, so it's okay if you don't understand this. But even when the field theory is free, in other words, even when the field theory is quadratic, regularization is necessary to calculate expectation values of composite operators. To explain why, roughly speaking, this is for people who have some prior quantum field theory knowledge, so it's okay if you don't have no idea what I'm talking about. But if you were to calculate phi x squared, if you were to take this in Feynman diagram language, you would have like a closed loop. And you know that basically closed loops leads to integrals over momentum that might diverge as so. So yeah, that's basically the reason. And let's see. Okay, so I guess that's point number 2. Point number 3 is dealing with Jacobians. Are a bit weird, but not that weird. I mean, you can still work with them.
Jacobians happen when the Jacobians are involved when you change the coordinate basis, right? From let's say the polar coordinates to the Cartesian coordinates. But what would it make? What would it be in the context of functional analysis?
So like we're okay. So we're doing something like this, and so let's consider 2 cases. The first case is multiple cases. The first case is when phi is just phi plus a constant. Well, not constant, but this is just a function independent of phi. In this case, this is like taking a vector and translating it. So basically d phi is equal to d phi. This is actually kind of useful. It's a kind of a useful. And the second one, I guess. Oh, we could try. In dividing the ward identities.
Okay.
These are important. But they're also kind of hand wavy. But anyway, like the second method of doing things, I'm gonna consider an example that is actually kind of sus in the sense that it is kind of weird.
Going back going back to the first one for translations, would a Jacobian be just one? Because in the case in multivariate calculus where you just have
it's
translations,
one.
the Jacobian is one. Yeah, okay, so
Okay,
okay,
so
great.
let me try something weird. Let's try phi prime equals h phi, where h is a function independent of phi.
A sort of scaling, right?
Yeah, this is scaling, but things might get a little intense.
I see.
So we see that things might be weird. Because basically you have to, the Jacobian is basically you have to take the limit if you were to consider the lattice case again, where n and a and b go to 0, there's basically a product. Okay, so let's rewrite this a little bit. Let's verify is h phi prime. Okay, so the Jacobian in this case is going to be basically the limit of all the h's like multiplied to each other. If you were thinking, but then you're
sorry, just to clarify, the Jacobian is a matrix of basically partial derivatives of phi prime with respect
oh
to
yeah, I was talking about the
yeah,
determinant of the Jacobian.
Okay, sure.
Wait,
Okay,
let me just write that j here and that j here. Okay, now we're good. Okay.
Okay, yeah, great.
But the thing is, if you take this limit, then there is a lot that's being multiplied. Right, so if you're taking the limit where the lattice spacing goes to 0, this is infinitely many things multiplied to each other. So in a sense, this diverges, so we need to regularize it. Okay. So we can actually try this out. Yeah, we could actually try this out. So let's actually try and do this. So let's calculate the Jacobian. Recall that in like the multivariate calculus, the Jacobian is a matrix, so we can give it like indices like so. In the current case, in the path integral case, the Jacobian is going to have x and y two. Okay, so maybe that wasn't the best. Let's see here. The Jacobian is going to have two coordinates as indices, where x1 and x2 are both in R2. Okay. And let's see here. So Jij in the multivariate case is equal to partial phi, partial, what would we call the variable zi partial z prime j or something.
Yeah, that makes sense.
Here jx1 x2 is equal to partial phi x1 or partial phi prime x2. I guess you could say that. But actually, this is not a really good way to write things. Because if we're taking like derivatives like this, we should actually use the language of functional derivatives. So we're just going to write down the definition of functional derivative here. So basically, if f is a function of some other function, and if a small change in f is written as the integral over a small change of phi prime as so, where there is something here. we write this as basically delta f delta phi prime at x. Or in
If I can perhaps draw a parallel with multivariate calculus, because I realized that it tends to help. So df tends to, in multivariate calculus, this would be a sum over basically all the partial of f with respect to some coordinate xi and gxi, and this sum becomes the integral, or a better written, right? We are basically this thing is basically corresponding to the gradient of f in some sense.
Right, yeah, it's the exact same thing.
So yeah, okay. Please continue.
So we should actually kind of rewrite this thing. And so if you like take a long, sturdy look at this, you can actually interpret this as, roughly speaking, okay, this is bad notation. This is terrible notation. You can think of it as the square of the delta function at 0 times partial f partial phi prime at x. Why? Because like you use this parallel. So we should be able to write this. This is bad notation, but you should be able to write this. So this is bad notation even by physics standards, but you should be able to write this as the sum over delta phi prime at x and partial f partial phi prime x, and a sum over x, which is different from an integral over x. The difference is that the integral the difference is that the integral over x, okay, so let me explain it this way. The integral over a delta function is 1, but the sum of the value of the delta function at all values of x is delta 0, because it's only non-zero at delta 0, and we're taking the sum of that.
Right. So when going from the integral to a sum, we need to basically put in a factor of delta 0.
Yeah, we need to put in a delta 0, a factor of delta 0. So basically, the integral these x is equal to 1 over delta 0 sum over x's. This is terrible notation.
It's kind of similar to the to how when we have the sum over in condensed matter, we always have a sum over momentum the momentum variable, right, over some quantity, and when we convert it to an integral, it becomes integral over dk over 2 pi. And I guess the interpretation is because it's 2 pi over here and not delta 0.
No, I think it's because keep saying, and I'll see if what you're saying is the same to what I'm thinking.
Sure, because essentially this is the volume of the space of case, and the volume of the space of case is periodic, so it's 2 pi, it's compactified, right? So in this case, where it's not compactified.
Wait, is it? No, I don't think so.
Okay, sure.
I think I can draw a parallel though.
Sure, okay.
In the K example, the correct way to think about it, I think, is dk. There is a 2 pi factor somewhere. I'm not sure if all the factors are correct here, but like you could actually try doing dimensional analysis here. If you do dimensional analysis, this is proportional to L minus 1, but this is proportional to L0. So you need to include an L minus 1 factor here, which is equal to the total length of the system, or this is equal to the volume of the system. And if you were to take the limit where the system is not, so the system is like a periodic system, that it would be the volume of that system. But if you take the limit where the volume of the system goes to infinity, this goes to infinity, so we can see that this abruptly becomes delta k equals 0. I guess.
I see. Okay, so that makes sense.
Or like 2 pi. Yeah. But anyway, yeah. But this is all really terrible notation, and you should never use this. So we should actually never talk about. Could you go up a little bit? You should a little bit more. Above functional derivative. Okay, cool. So you should really never talk about this. Really never use this. It's a bad idea. So let me just write down. So it's delta 0 over 1. Delta square 0 over 1, delta f, delta phi. No, wait. So yeah, phi is 1, delta phi prime x2. You should never use this because it contains illogical delta 0. Instead, you should use this instead.
Okay, sure.
And using this, I'm actually going to create a formula for the determinant of the Jacobian. Okay, so let's see here. Cool.
So essentially, the Jacobian has this factor of 1 over delta squared, which is responsible for, previously we mentioned there's a product over all of h.
Right? Yeah.
So essentially this product over all of h, the infinity that appears here, is kind of due to the delta squared.
Wait a minute, is it? Let me think. It is. Is it?
So if basically
no, actually, I'm not sure.
Okay, sure.
There will be like other divergences that kind of cancel with this guy.
I see.
Okay, so let me keep going because so let's see where. So let me tell you exactly what I'm trying to do here. Is I'm trying to find a formula for to the very down. Okay, so trying to find a formula for d that j, where j is equal to, I'm gonna write delta 0 j is equal to delta phi delta square 0 j is equal to delta phi x delta prime 1 x2. Okay. So I'm gonna do this generally. So okay. And the key to doing this is using the fact there are many ways to do this. Okay, but like the general case would require fermionic fields. Like you usually use things like ghost fields to do this, but that is kind of beyond the scope of what we're doing today. So I'm just going to not do the general case, and I'm just going to do the delta phi, the phi equals h phi prime case. Yeah, and maybe in this case we will see that what you just said, the delta square 0 is actually equal to the inverse of the lattice spacing. Maybe we'll have to see. So in this case, the determinant of the Jacobian is basically equal to the products at x, and then we have partial x phi x partial phi prime x. This is equal to basically hx at all the points. we could write this to the exponential of a sum. This becomes the sum over x, and this becomes log of hx. And now we're going to change the sum to an integral. But to do this, we actually have to include the delta squared factor. Then we have ln hx. And then we have d squared x. Oh, so you're correct. The delta squared term.
It is responsible.
Yeah, it is responsible in this case. And so I think the key idea here is that we started with like something that is really terribly defined, and we were able to kind of distill that terribleness into the square of the delta function.
I see.
And we can actually calculate this using dimensional regularization. So we can actually calculate this. The idea is to, instead of calculating this, is to calculate delta 2 minus epsilon 0.
I see.
So let's see how this could be done. So delta 0 can be written if you do a Fourier transform.
Right.
Wait, let me just. So let's see. Okay, so this is the fun part actually. It's not going to be easy to understand, but that is because this is not well defined. So this is why mathematicians have no idea what physicists are doing, because physicists themselves have no idea what they're doing. But it's like a culture, you just have to like get used to the rules. So so delta of x, if we use Fourier transformation, is equal to dk over 2 pi e to the ikx.
Right.
Delta squared x, wait, not that, but delta x, so delta 0 is equal to n1 over dk 2 pi. Delta squared 0 is equal to d squared k over 2 pi squared. So delta d0 is equal to integral d dk over 2 pi to the d, for at least d equals integer. And we can write this using the radial component of k and the rest of it. So we can write k is basically a d-dimensional vector, k1 kd. We can write the absolute value of k. We're just going to write that as k. And this is basically integrate. We can like separate this. You can do this radially. So you can write this as basically integral over dk and d some kind of omega, and then that would be proportional to the k to the d minus 1. And this is omega d minus 1. Yeah. And this is so 2 pi d.
In the case of polar coordinates, it will just be rd theta, this part.
Yeah. And we can actually just integrate over that, and we're just going to call the total stirred angle omega d minus 1. I think this has to do with the gamma function. I think that's where the gamma function comes out of. Let's see if my memory
comes out from the volume of spheres, basically.
Yeah, the volume of a sphere.
Gamma function calculate volume of sphere.
Right. Let's see. Could you like do a Wikipedia search? I'm actually really enjoying this aspect where you can just search Wikipedia in real time. Could you do a Wikipedia search on calculating the higher dimensional sphere volumes from the gamma function?
Volume of sphere.
Let's see. Okay, yeah, nice. Okay, so we have that. This is nice. Wait, it's a ball though, right? What we're really looking for
is a shell, right? You're looking for a shell.
Yeah, but we can just take the derivative of r, so it doesn't really matter. If we take the derivative of r, it becomes pi over d minus. Wait, so just taking the derivative becomes pi d over 2. And then there is a.
Is it d minus 1 over 2 or is it d over 2?
Well, it's d over 2 because by d minus 1, I was talking about the shell, which is d minus 1 dimensional, but it's the shell of a d-dimensional ball. And I'm taking the derivative of that Wikipedia formula. So this is probably going to be
okay,
correct.
sure. That makes sense.
And then we're just going to have a d here, and then gamma d over 2 plus 1, hopefully. But I know for a fact that the answer to this is going to be decently simple. So k d minus 1 dk 2 pi d. Okay. And
how about
then
this other factor of so one of the k to the d minus 1 comes from differentiating r to the n, but you have another
the
term.
k. You can understand it just by, I understand it basically like the shell getting bigger, and it's proportional to k.
I suppose this term over here is equals to
Yeah.
this over here.
No. It's equal to not. Oh, it's not k to the d minus 1 is not included.
Oh, I see. So
by omega, I was just meaning like the volume of the unit shell.
It basically equals to this component.
Yeah.
Oh, unit shell. I see.
Yeah,
okay. That makes sense. Yeah. So you basically substitute.
Yeah.
Over here you did substitute r equals to 1 because of the unit shell. Okay. Yeah.
And basically because we're gonna analytically continue this, we're gonna calculate. We can do the integral over here by assuming that it is a convergent integral. And this is just equal to well, because integral is 1 k d. Wait, this is actually. Oh, right. Darn it. There is another subtle issue here, which is kind of annoying. So, wait. Let me just think for about 20 seconds. Okay, good. So there is a subtle error here. There's a subtle issue here. The issue, you can see that if you try to integrate this, dk, even in the case where 1 minus d is like a big number, it's like a positive number, this thing still has issues because of integrating to 0. And that is kind of like a different thing. That is actually not coming from the infinite lattice limit, or I guess like the 0 lattice spacing limit, but that is actually coming from that's actually coming from a different reason. That's actually what is called an IR divergence. And it is something of a slightly different nature. To actually cure this one, so let me explain where this divergence is coming from. This divergence is actually coming from.
Oh yeah, sorry to remind you, but I gotta go maybe in about 7 minutes. Yeah.
Okay, cool. Yeah, if we don't finish, I'll try to find a nice place to like finish it in about 3 minutes. So this divergence is coming from the infiniteness of space. And so if we were to place R2 in like a box, so if we were to have a box with boundary conditions in R2, a compact region, this divergence would not have happened. But curing this divergence is another topic. I guess I'll continue this story in the next video. So yeah, I'll leave it there.
Okay, cool. So
yeah.
in summary, we have in order to find so we talked about this because we were trying to find the determinant for J.
Yeah.
And we've isolated the nasty part which blows up.
Yeah.
And now we're trying to regularize the nasty part.
Yeah.
By using the d minus epsilon prescription.
Right.
And that led to the discussion of performing this delta squared integral which we are doing generally, and that leads us to this place where basically the divergence comes from the infiniteness of space. And if we're able to put a boundary on it, then that would probably.
So currently right now, if like we cured the delta zero divergence using analytic continuation. So we already cured that. But there is another hidden divergence which is coming from the infiniteness of R2. But that is easier to deal with. That is what is called an IR divergence. So the delta zero divergence coming from the continuousness of space is called a UV divergence. But the divergence coming from the infiniteness of space is called an IR divergence. So yeah.
Oh, okay, cool. So basically the UV divergence comes from the fact that you can divide space to very, very small quantities. And hence, so in some sense, higher wavelengths, small and smaller wavelengths, higher and higher energies, which corresponds to UV.
Yeah.
But the case where infiniteness of the space in terms of you can go infinitely in one direction comes from the fact that your functions can have very large wavelengths.
Yeah, exactly.
I see. Okay, that's cool. So I see there's a difference between those two divergences. So we have cured the UV one. How exactly have we cured the UV one using?
Well, okay, so you can look at this integral actually. So if you look at the final integral that I wrote, it contains both the UV and the IR divergence. So if you have the infinity one here, this is the UV. K is like a wave number.
But this UV plugging in infinity doesn't cause it to.
Well, okay,
diverge, so does it?
Here's the thing: if 1 minus d is negative, right, this thing would diverge. So we're curing the UV divergence by analytically continuing to where there is no UV divergence.
I see.
But then we still have the IR divergence, and I'm going to explain how we're going to cure that next time.
I see. Okay, cool. This has been fun to do. Thanks.
Yeah. Okay, so have a good one.
We'll
see you next
time. I think
time.
that's a good place to start. Yeah, thank you.
Okay.
Thanks for joining. Yeah, have a nice day. Bye.
Bye.